Hi there, welcome to our class. For today, we are going to discuss the introduction to data structures and algorithms. So, before we get into that, let me start with asking some specific questions. Like, how many cities have highest crime rate here in the Philippines? Another is, how many people here in Davao City were fully vaccinated, including the data on how many got inoculated with COVID vaccines, such as Sinovac or Sinovac, AstraZeneca, Pfizer, and etc. To answer questions like this, uh, it is not enough to have the necessary information. We must organize that information in a way that it allows us to find the answers and time and satisfy to actually satisfy our needs. Representing information is actually fundamental to computer science. The primary purpose of most computer programs is not to perform calculations, but to store and retrieve information, usually as fast as possible. For this reason, the study of data structures and algorithms that manipulate them is at the heart of computer science. And that is what this course is all about, helping you to understand how to structure information to support efficient processing using earlier and the latest functional data structures and algorithms. A good algorithm usually comes together with a set of good data structures that allow the algorithm to manipulate the data efficiently. In this course, we consider the common data structures that are actually used in various computational problems. Specifically, for this chapter or this week, you are expected to understand the underlying concepts about the data structures and algorithms, to identify different types of data structures and its characteristics, and to discuss the need for choosing and selecting the appropriate data structures. And last one is to determine the data structure philosophy. So what is data structure? As you can see here in our matrix, for Tana is obviously of type string. And then we have here, along with it, is 7 is an integer type, probably. And the 7,500 with decimal point is actually either a float or a double. We can actually organize this data as a record. Like we can say this as a pet record, which will have the pet's name, pet's age, and pet's price. Now we can collect and store these records in a file or a database as a data structure. It is actually similar to a class concept in your OOP course, where it collects the different types of data under one or under single entity. However, data structures provide techniques to access and manipulate the data efficiently. In a simple language, data structures are programmed to store data to store order data so that various operations can be performed easily. It represents the knowledge of data to be organized in memory, and it should be designed and implemented in such a way that it reduces complexity and increases the efficiency of the program. So here are the types of data structures. For some reason, anything that can actually store or can store data can actually be called as data structure. This could be integer, float, character, boolean, what else? Short, byte, especially in Java, and which are actually these are actually best known as primitive data structures. So this primitive data types are actually explicitly declared in most especially in Java, in C and C++, and even in PHP, where actually in Python it is not declared explicitly. I mean, you don't have to define explicit data type for once you declare a variable because it is a dynamic type programming language. Okay, so They in on the second side of our of the data, not data structure type is actually an ADT type. So they are complex by nature and are used to store large and connected data. Some examples of this data structures of this ADT data structures are actually stack, queues, trees, graph, arrays, list, array list, vector in Java, and dictionary sets in Python and all that. And these things are actually discussed in the next chapter. So all these data structures allow us to perform different operations on data. We are going to select these data structures based on which type of operation is required. We will actually look again, as I've said, we will actually look into these data structures in more detail in our next lesson. Now, here is the classification of data structure. So we have here linear, nonlinear, homogeneous, non-homogeneous, and we have also here static, and we have here dynamic. Now, let us discuss it one by one. So again, the data structures can be also or can also be classified as with the following or based on the following characteristics. So in a nonlinear data structures, the data are actually arranged in order. So example of it is are actually arrays or arrays, stack, queue, and linked list, which will also be discussed in the next chapter. And then we have nonlinear. We have tree, graph, tree, heaps, and matrix. So nonlinear data structures. It's a it's actually the items or the data are not arranged in sequence or in order or non-ordered linear structures. Now, homogeneous rather data structures, it means that all the elements are of the same type. So one example, best example to that is array. And for non-homogeneous data structure, the elements may not or may not be of the same type. So some of these are actually concepts that can be found or written in C++, like structure, record, and union, and also and classes. Um, in Java, it's all about like classes or enum or enumeration. Now, another one is static. So static data structures are those that that will not or whose size is actually fixed, and it's uh, it's not being it's cannot grow and shrink its size. So again, it's fixed. So one example or best example to that is actually array. And then the last is dynamic structure. So when we say dynamic structure, this is a data structures that can actually grow and shrink its size during the execution, like pointers in C++ and linked list in Java, right? So these are the classification of data structures. So we can say that many data structures have the same organization of data at the memory level. Still, they can provide the different functions and operations that differentiate from each other. All right, how about algorithms? So come consider the set of instruction to preparing and cooking chicken adobo. By the following things in order, even though you haven't cooked this yet before, you would be able to arrive what it's like to have such delicious recipe. So basically, an algorithm is a finite set of instruction or logic when written in order to accomplish a certain predefined task. It is actually not the complete code or program, but it is just core logic of a problem expressed either in as an informal high level description like pseudocode or using or when you are going to use flowchart, which actually which was actually discussed in your previous programming languages or logic formulation. In the simplest words, algorithms is nothing but a sequence of steps to be followed to solve or any problem or to achieve desired input. Okay, so an algorithm takes the input to a problem. Normally, it's like written in function and transform this into an output, which is basically a mapping of input and output. Just like our example here, we have here a procedure or step, which is the function and arriving the final recipe by following certain procedure would mean arriving the output as a tasty dish. Note that a problem can have many algorithms. So as procedure in cooking chicken adobo, it can also have different algorithm or steps or procedures. It varies depending on the person or a culture, especially here in our country. There are various ways of preparing such delicious food to serve in our table. Okay. Now, what are the properties of algorithm? So let's start with the number or the first one, which is input. Input means there should be zero or more inputs supplied externally to the algorithm. So normally it's a data. Okay. Output. What do you mean by an output? There should be at least one output obtained. It can be an information about being processed by an algorithm or such that. Next is the definiteness. When we speak of definiteness, every step of the algorithm should be clear and well defined. Should be again clear and well defined. And then next is finiteness. The algorithm should have a finite number of steps. Okay, so it has to have a certain steps, and these are the steps and procedures that are needed to be followed. And then we have correctness or correctedness. It means that the every step of the algorithm must generate a correct output, or we should have arrived a correct or an accurate output. And then lastly, we have computer implementable instruction. Of course, as we are talking about computer science related problems, uh, the steps should be understood by the computer. All right, so what are the examples of our algorithms? Excuse me. So here we have sorting algorithms or sorting techniques. We have some examples here. We have merge sort, quick sort, team sort, bubble sort, selection sort, insertion sort, and we are going to discuss that one in, I guess, in week 3. Next is we have searching. We have linear search and binary search. So normally it's linear searching. We will be modeling like the linked list. Okay, for binary, we will be modeling the trees. Okay, and then we have the shortest path, which are the examples here are Dijkstra algorithms, Bellman-Ford algorithm. So some pronunciation, I mean in some other countries they pronounce this as Dijkstra or Dijkstra algorithm. It depends on what nationality you are in. So the Dijkstra or Dijkstra algorithm is actually an algorithm for finding the shortest path. So like normally it's applied in a map, to navigate from one place or to traverse from one place to another. And then we have Billman-Ford. Billman-Ford algorithm is actually an algorithm that computes the shortest path to evaluate and assess whether that's actually the shortest path. Okay. Next is how about the efficiency of an algorithm? So an algorithm is efficient and fast, and if it takes less time to execute and consumes less memory space. There are actually two properties to measure the performance of an algorithm. Number one is the space complexity. So when we say space complexity, it's the amount of memory space required by the algorithm during the course of its execution. And when we say time complexity, it's the amount of time required by the program to run its full completion. So what are the need for data structure? So why do we need data structure? Why do we implement data structures? Why do we maintain data and information using specific or certain data structure? So you might think that as computers get more powerful, program efficiency becomes less important. After all, it's the processor speed and memory size keep getting better. Can the hardware of tomorrow solve today's efficiency or efficiency problems? As we develop more powerful computers, our story so far has been to use additional computational power to solve more complex problems, be it in a more complex user interface, a larger scale of problems, or what were previously considered problems, like new ones that are computationally unviable. So basically, more problems requires more calculations, which makes the need for efficient programs to even like greater. So unfortunately, the as task becomes more and becomes more complex, they become less and less like in our daily experience. Therefore, today's computer scientists must be trained to gain a deep understanding of the principles behind efficient programming because their daily life experience is actually often uh, not applied when designing computer programs. So basically, a data structure is actually more concerned primarily relating to the efficiency. The more our data is organized, it means that it can be more efficient programs. Excuse me. Another one here with enough space to store collection of data items. It is always possible to search for specific items in the location, print or process data items in any desired order, or modify the values in any specific data item. The most obvious example here is an unsorted array containing all the data items. So all necessary operations can be performed on unsorted arrays. However, using the correct data structure can distinguish between a program that runs for a few seconds and a program that takes many days. For example, looking for a specific record in a hash table is actually much faster than looking up in an unsorted array. So basically, choosing data structures and algorithm can make the difference between a program running in a few seconds or many days. So, needless to say, people write programs to solve problems. However, programmers sometimes forget this. Therefore, you must keep this in mind when you are going to choose a data structure to solve a particular problem. Only by first is by analyzing the problem deter to determine the performance goal to be if to be achieved. Can it be uh, hope that the correct data structure will be selected for the job? So bad programmers ignore this analysis or a step in analyzing and apply a data structure that they are similar with but not suitable for the problem. The result is usually a slow process. In contrast, using complex representation to improve a program that can meet its performance goals when it is implemented with a simpler design is actually meaningless. When selecting a data structure to solve a problem, you should follow these steps. Number one, excuse me, analyze the problem to determine the basic operations that must be supported. Second, we have to quantify the resource constraints for each operation. And the third one is to select the data structure that best meets these requirements. So basically, these first three steps approach to selecting a data structure operationalizes a data-centered view of the design process. The first one, which is the analyze the problem, is actually concerned for the data and the operations to perform on them. The next one is actually the representation for those data. And the third one is actually the final concern, which is it's actually the implementation of that representation. So typically, if we want the simplest data structures that will meet the requirements, these are some of the questions that we might ask often to help to narrow the possibilities. Are all data items inserted into these data structures at the beginning, middle, or in the end? Can data items be deleted? If so, will this make will this probably make the implementation more complicated? Number three, are all the data items processed in some well-defined, or is search for specific data items allowed? So random access can, I mean, in a random manner, search generally requires more complex data structures because again, it's random. So each data structure has associated costs and benefits. In practice, it's hardly ever true that one data structure is better than another one, the other for use in all situations. If one data structure is actually or algorithm is actually superior to another in all aspects, the inferior one will actually or usually have long been forgotten. So here, the data structures must provide a certain amount of space for each data item that actually it stores, a certain amount of time to perform a single basic operation, and a certain amount of programming effort. So each problem has limitation of space and time available. The solution to each problem uses basic operations in a certain relative proportions, and that data structure selection process must take this into account. Only after carefully analyzing the characteristics of the problem can we determine the best data structure for the task. So here, note to every programmer out there, like the the very goal of learning this course is actually to reinforce the concepts that there are costs and benefits for every data structure, which must be a worldview to adapt, learn the commonly used data structures. This forms this form a programmer's basic data structured toolkit in which we can select the appropriate data structure and algorithm, and to understand how to measure effectiveness of a data structure or a program. So these techniques also allow you to judge the merits of the new data structures or the new ones comparing to the others that might have the that were invented before, and the new ones that are that might be invented tomorrow or in the future, which is to actually prepare you in the future. So as a summary, we have here a data structure is about organizing and managing data effectively in such a way that we can perform basic operations efficiently, while an algorithm is actually a step-by-step procedure to be followed to reach the desired output. To secondly is to understand the data structure in a meaningful way. You also have to consider the understanding of memory allocation and space and time complexity to perform a specific operation on it. We have also to note that different data structures can use the same internal memory management and organization, but they can differ by the functions they are providing, which can be used to solve a specific class or problems. And the fourth one is steps in algorithm can use one or many data structures to solve a problem. And lastly, we have the steps in algorithm can uh, actually use or many data structures. So I guess that would be all for today. And thank you guys for listening. Have a great day. Bye bye.